Hey guys, so in this video we're going to go over how to draw a Cassegrain telescope and then what CCDs are. Okay, so what it says here is draw a ray diagram for a Cassegrain telescope. You have to remember there's two telescopes, the normal adjustment telescope that uses refraction, so it uses lenses, and the Cassegrain telescope is the one that uses reflection. So if it does reflection, that means it uses our mirrors. Okay, so when I draw a Cassegrain telescope, you have to make sure that you always draw it a parabola in shape and not spherical. Okay, because remember, they make them parabolic in shape to avoid spherical aberration. You have to make sure that you draw one straight, smooth curve, and then you're going to use a rubber to rub out a little hole in the middle that the light rays can lay through. If you draw two separate lines and it's very obvious in your test, they will take a mark off you for that, okay? You have to be careful that you draw one smooth line and then use a rubber to rub it out, okay? Then what you're going to do is you're going to mark your principal axis along the middle of it, going through that hole. And you're going to label this one as a mirror. So I'm going to show that that's the back of my mirror. And it's the primary concave mirror. And what's going to happen is you're going to draw your two rays coming parallel to your principal axis, but you'll have a ruler. And you know that when they hit the mirror, you're going to draw on your normal, and that the angle of incidence is always equal to the angle of reflection. Draw my normal. My angle of incidence is always equal to my angle of my reflection. So that's a bad one, sorry. So you have your ray coming in, draw your normal. Angle of incidence is equal to the angle of reflection. So then I've got my two rays now coming out. And what's going to happen is they're going to hit this secondary convex mirror. So they're going to hit a secondary convex mirror. And you need to show that they are going to be reflected and they're going to cross each other in that gap. Okay, so see how mine crossed there just before it. So you need to use your rubber and you're going to go again to make sure they cross at the gap. So again, what I need to do is make sure that they cross at the gap. Okay, so they're my rays crossing at the gap. For this one, you only need to draw two light rays. So I'm going to show those my light rays going in. And again, they hit the primary concave mirror, get reflected onto the secondary convex mirror, and then they go cross here. And then over here is where you'll have your little eyepiece lands. Okay, next one says telescopes have two options. You can either have your telescope, so we've got our telescope, and either I can actually have a human here using my eye to look through the telescope at my distant stars, or what I can do is have these things called CCDs. So CCDs are basically just this like cross-sectional area, and it's divided up into pixels. And every pixel can basically detect a ray of light. Okay? So what's happening is you're comparing how is my eye better or worse than using CCDs. And hopefully you're thinking, of course it's probably better to use CCDs because the human doesn't have to actually be there. So if the human has to be there, and let's say I want to observe it for an hour, I have to stand there for an hour with my eye on it observing it, okay? Whereas CCDs can just collect the data for a long time. So one advantage is we can collect light for a longer time, okay? Or we can have, another way of saying that is just a longer exposure, which is going to result in us getting brighter images with the CCD, as no human has to be there, right? Because you might have to go to the toilet, you might have to eat, right? Another thing that we can compare is that CCDs have a better quantum efficiency. So what is quantum efficiency? Quantum efficiency looks at how many photons, so the number of photons, so photons measures as particle of light, the number of photons that are actually detected over the number of photons that arrive, right? And for a CCD, that quantum efficiency is over, but just remember the number 80%. So 80% of the photons, those packets of light hitting that CCD, can be detected, okay? So 100% is what hits it, 80% of them can be detected. But for the eye, it's only around 1%, okay? So that's so little. So quantum efficiency of a CCD is much greater, it's around 80%, whereas for the eye, just learn the number that it's around 1%. So clearly the CCD is better quantum efficiency, okay? Other things we can't really compare, we can't change the diameter, so it doesn't matter about the diameter because we're using that same telescope. Because remember, it's just the eye is at one telescope or the CCD is at one telescope. What else can we compare? So again, what I was thinking about is the first thing I was thinking about there was the power. But again, power is proportional to the diameter squared of that telescope, which we can't change. And the other thing we look at telescopes is that we look at the minimum angular resolution. So minimum angular resolution is the wavelength divided by the diameter. So again, I can't change the diameter of the telescope because again, it's just the eye or the CCD we're placing here that's changing. But think about the wavelengths now. I know the eye can only detect visible light. So the eye can only detect visible light. But if we use CCDs, we can take a wider range of wavelengths. So CCDs can give us a wider range of wavelengths. So we can observe the stars with a range of wavelengths. Maybe we want to look at the IR spectrum. Maybe we want to see how many gamma rays it emits. We don't only have to look at the visible